All right, now let's try to make sense of the bigger picture and try to connect all the pieces of the puzzle together and try to see if it makes sense how our use case of default detection or default prediction works in a industry setup following the best practices of MLOps processes. The goal is to predict a loan defaults reliably in production, right? So the main life cycle has been split into three phases. The first phase is obviously building the model, where we prepare the data and train a model on that data to see how well it predicts on the defaults. And once we are happy with the model, we register it in a model registry, and basically then we serve the model via a fast API service or an inference engine. That is up to us how we want to serve it. And then the third main pillar is monitoring the service and also the model performance in a production environment, because we always want to make well informed decisions, right? Now if I can make this chart a little bit bigger and let us focus on the model development phase and the model service serving phase in this session mainly. So on the left you can see that the data and the training config we use for training a particular model can live on a cloud bucket. It can be a S3 bucket or GCP, it can be anything. Now here a containerized training pipeline prepares the data, trains a random forest model on that data, and logs everything into MLflow. We follow a parent-child hierarchy in terms of logging the data sets and the model artifacts that we will discuss as we move ahead. So now the training block isn't one of for Crest's default prediction model that uses a random forest model, but it actually follows a standard training SOP that we can use across multiple projects across different models. Let me unpack how this works. Actually, the SOP defines one of the reusable training patterns that we can use for any model type. It can be tabular, text, vision, whatever the team is building. The shape is always the same, right? We want to follow the three basic pillars of training, and that is data preparation, and then training the model on the prepared data, and then evaluating the model, right? And the best part is each of these steps are exposed as its own independent CLI inside one single Docker that can be run in sequence or that can be run in any other order, as these steps are mutually independent and exclusive. And as the data between these steps are not handed over manually, so these steps can be run in any combination. But in order to follow a proper happy path training mechanism, we should like to follow these steps in this sequence of preparation of the data and then training and then evaluation. But in terms of fine tuning or just evaluating some other models, we can skip or add more steps in between. But these are the main three pillars, right? Mm. At the end of each step, files are never handed over to the next step manually. MLflows carries the state. Basically, everything is logged after each state into MLflow independently. We follow a parent and child hierarchy that I mentioned before. The parent run actually captures the data set on which we want to train a series of different models and flavors. And basically we have a child run under that dataset parent run, on which we train and evaluate different models on that particular dataset, right? Now basically in production our orchestration tool like Airflow or ECS just can simply trigger those commands whenever needed via that Docker engine, and everything is logged under durable storage and MLflow. So every step is independent of each other. Now let's try to see how our use case fits here in this training and inference serving. Now let's talk about our Crest's loan default pipeline. So it is one concrete instance implementation of the training pattern that we just discussed. The mechanism is generic, only the models, implementation and training logic and the config changes per project, right? So in our case, suppose we have to build a default prediction system using a random forest. So first of all, we create the training code and everything following the universal training SOP that I just discussed below. And once I have the training code, uh, I would like to keep the code in a repository, ideally in a separate repository in GitHub, where we maintain all other training modules, let's say for scam detection or other bank fraud detection or different kind of image detection model. It can be anything, but we have a separate repository in GitHub where we maintain all the training logics, right? So as soon as we push the code in GitHub, we maintain all the iterations of the code with different versions, with Python poetry versioning and stuff like that. So every change and push into a GitHub comes with a PR and with a version change for a release. And whenever we release a version of a code, the GitHub actually has CI/CD actions for the repository that actually builds the code into a Python package. And basically, we'll have our private code artifact repositories where we keep our private Python packages that can be used within the organization. And once the Python package is built and pushed into the private package artifact, the CI/CD action will trigger a build of a Docker with that Python package, so that the Docker can be used by any environment. It can be a AWS ECS service or a task or a Kubernetes environment, that doesn't matter. But basically, the CI/CD builds the Docker and then it pushes into a private Docker repository from where it can be accessed later. Right. Now we come to a second player, that is we maintain another repository that is that contains all the infrastructure as code configurations. So basically, I am talking about a second repository where we maintain all kind of configurations related to infrastructural requirements that we maintain via Terraform code. Basically, how we want to pack this Docker and serve this Docker. We want to serve this Docker as a task or a service. What is the resource we need to run that task? Where we want to run that task? All these things we can keep in a separate repository. And basically, there we build the task with the environment where we want to run this Docker repo of this training, right? And once we create all our configuration wise code, which will enable us to run this Docker image in our desired environment, we push that changes in the GitHub again with a different repository for infrastructure as code. And that GitHub repository has its own CI/CD actions that will trigger a automatic deployment action via Spacelift or AgroCD or tools like that. And basically, in turn, what it will do is basically pick up all the configurations and resource needed to run the Docker in the environment, along with the Docker's URL and everything. And basically, it will create ECS tasks or any kind of GCP task or some kind of task that we can just trigger via orchestration tool. So now we have training code. We have the training code packed in a Docker. We have the infrastructure to run the code. And right now we can just go, let's say if we want to run it as a ECS task, we can just go to our AWS account, check the ECS task, check the commands, and the commands are mutually exclusive. I told like the preparation, training, and evaluation step. So via Airflow, we can manipulate the sequence of those commands, how we want to invoke the Docker for training, and basically then we can have our orchestration tool where uh, it can listen for new raw data to be put into the S3 bucket. We'll just come in some time how we are visioning that. And basically, once it finds a new raw data in a S3 bucket, the Apache Airflow can just trigger the training operations via ECS operator or something like that. That enables us to actually automate the training process completely. Now, once we have everything in place, now we want to start the training process. Now normally what we can do is the first process is data collection. If we want to train a model, so it can come from internal DB, production data, stuff like that, and basically we either keep the collected data in a cloud storage, or we directly pass it for prepare data clearance or cleaning of the data for annotations, because some of the model training needs labeled data, and we want human, maybe we want, say, in some cases human annotations for those data. So basically we can clean the data and put the data inside the cloud, and basically then we can use a lot of annotation tools that can actually annotate the data and put labels on them. And basically once the annotation process is done, they can actually store the annotated raw data inside the S3 bucket. So now once the Airflow sees that there is a new data in the S3 bucket, it triggers the entire training process that triggers the universal training mechanism for Crest, that starts with pulling the data and the data preparation config, along with what is the training model and model configurations and everything. It prepares the data, it pushes the data into a parent run, and then it passes the run name. It pulls the data from that run name, it starts a training, it pushes the data into one of the child runs under the parent run, and basically then it evaluates the model, and in this way we train different flavors of the models. Yes. So now once the training process is done and we have a lot of models from where we can choose from, so we want the team to review those models, and once the team reviews the matrices and manually promotes the winner model to the model registry, we would have a separate inference service that would pull the model from the model registry. In this case we are talking about MLflow. We maintain service config where we can actually mention which model and model version to pick up, both for the services or the tasks from the model registry, and we can control that when we can update those models using this service config, and basically this is how we can serve it. Now similarly we need to serve this model, and now we prepare service code that I can show. So for example, the training code lives here. So this would be one repository where there would be multiple trainings, not only train default training, but there would be multiple steps. And then in another repository there will be a service that will actually pull the model and serve it. So I am talking about this part here now. So once we create the service, we can also keep the code in a GitHub repository, and the GitHub repository, once we clear a PR and push the code into main, it can also have CI/CD actions that will similarly create a bundle inside a Python package that in turn will automatically trigger a Docker build and push into the Docker repository. we can use the same repository, but we can use different partitions also, but the idea is same. And then in the data IaC, as I said, we can create another service configuration or resources and environment where we want to host this service, basically in cloud or in K8 or stuff like that. And one thing, this data IaC configuration is one-time activity when we are creating a new service. Once that is done, we don't touch this infrastructure as code unless and until we want to manipulate or update the resources or try to change the auto scaling policies and those kind of things. Apart from that, data IaC is one-time update. And another time we only update this data IaC is when we change something logical in the code that requires a new Docker build. So we update the Docker image here manually, and or we can do it automatically also. So where was I? Yes. So once we similarly build the infrastructure for hosting the service on cloud, we can similarly the data IaC, we can push the code into GitHub, and then the configurations would again trigger a space leaf to create a service if it is not there inside the cluster. And if the service is already there, it updates the task definitions or everything that actually mentions the resources and stuff to run the service. And basically this is how we can run and serve a model end to end, right from starting from data collection, training, preparing the training code, and then how to orchestrate the training, automate the training, and then basically how we serve the models via model serving phase. And once this is done, this is another very interesting phase where we actually keep track of the matrices that the services generate about model performance and service performance, and we can monitor them in monitoring dashboards in Grafana, and then we can set alerts, and if anything falls out of the place, we can have those alerts in Slack, in our mail, wherever we want in our preferred channel. Yes, so this is one thing. Another thing is that, like, if we build our service configuration, service code in such a way that these service configurations are kept in cloud, so when we update a model, we just go to the service configuration file in the cloud, change the model version, and then just trigger a restart, and that will enable the service to fetch the new version of the model from the MLflow again without having us to rebuild the Docker and push the new image again. And any kind of changes that doesn't need code change or pushing of a Docker can be handled by hot restarts with update of a service. So yes, I hope this makes sense and this aligns well with our use case that was in our hand. Thank you so much. If you want to read more about the CI/CD ideas inside the doc, you will find the CI/CD release idea I talked about. And if you are curious about a bit more about how we can orchestrate or automate the training pipeline using Airflow, ECS, and S3, you can check out this document, the training orchestration. Apart from that, the main idea about model training, you can find it here under model training readme, and then there are the code bases under loan training default, loan training service. Yes, thank you so much.